Welcome back. This is Jeffrey Chang, and the topic we're going to discuss today from Algebra 1 is radicals and rational exponents. So here's the learning objectives. In this section, you will learn to evaluate square roots, learn to use the product rule to simplify square roots, use the quotient rule to simplify square roots, add and subtract square roots, rationalize denominators, and also using square root rational roots. So the first topic, evaluating square roots. When the square root of a number is squared, the result is the original number. Since 4 squared is equal to 16, the square root of 16 is 4. The square root function is the inverse of the squaring function, just as subtraction is the inverse of addition. To undo squaring, we take a square root. In general terms, if a is a positive real number, then the square root of a is a number that, when multiplied by itself, gives a. The square root could be positive or negative, because multiplying two negative numbers gives a positive number. The principal square root is the non-negative number that, when multiplied by itself, equals a. The square root obtained using the calculator is the principal square root. The principal square root of a is written as the square root of a. The symbol is called the radical. The symbol, this one, is called radical. And the thing inside, the number inside, is called radicand. And the whole thing is called radical expression. The principal square roots. The principal square root of a is the non-negative number that, when multiplied by itself, equals a. It is written as radical expression, with a symbol called radical over the term called radicand, like this. Here's a quick question. Does the square root of 25 equal to positive and negative 5? No. Although both positive 5 squared and negative 5 squared are 25. The radical symbol implies only non-negative roots, the principal square roots, and the principal square root of 25 is square root of 25, which is just positive 5 in this case. Next topic, using the product rule to simplify square roots. To simplify a square root, we rewrite it such that there are no perfect squares in the radicand. There are several properties of square roots that allow us to simplify complicated radical expressions. The first rule we'll look at is the product rule for simplifying square roots, which allows us to separate the square roots of a product of two numbers into the product of two separate rational expressions. For instance, we can rewrite square root of 15 as the square root of 3 times the square root of 5. We can also use the product rule to express the product multiply radical expressions as a single radical expression. The product rule for simplifying square roots says that if a and b are non-negative, and the square root of the product ab is equal to the product of the square roots of a and b, here. And the next topic, using the quotient rule to simplify square roots. Just as we can rewrite the square root of the product as the square root of the product of square roots, so too can we rewrite the square root of a quotient as a quotient of square roots, using the quotient rule for simplifying square roots. It can be helpful to separate the numerator and denominator of a fraction under a radical so that we can take their square root separately. We can rewrite square root of 5 over 2 as the square root of 5 over the square root of 2, like this. The square root of the quotient AB is equal to A over B is equal to the quotient of the square roots of A and B, where b isn't equal to 0, since the denominator couldn't be 0, or else it's undefined, or we couldn't find the answer for that. Rationalizing denominators. When an expression involving square roots radicals is written in simplest form, it will not contain a radical in the denominator. We can remove radicals from the denominator of fractions using the process called rationalizing the denominator. We know that multiplying by 1 does not change the value of an expression. We use this property of multiplication to change expressions that contain radicals in the denominator. To remove radicals from the denominator of the fractions, multiply by the form of 1 that will eliminate the radical. And next, let's continue. So, for a denominator containing a single term, multiply by the radical in the denominator for itself. In other words, if the denominator is b times the square root of c, multiply by square root of c over square root of c, which is 1. For a denominator containing a sum or difference of a rational and irrational term, multiply by the numerator and the denominator by conjugate of the denominator, which is found by changing the sign of the radical portion of the denominator. Like if the denominator is a plus b times square root of c, then the conjugate is a minus b times square root of c, like this. Using rational roots. Although square roots are the most common rational roots, we can also find cube roots, fourth roots, fifth roots, and more. Just as square root function is the inverse of the squaring function, these roots are the inverse of their respective power functions. These functions can be useful when we need to determine the number that, when raised to a certain power, gives a certain number. Understanding nth roots. Suppose we know that a cubed is equal to a. We want to find what number raised to the third power is equal to a. Since 2 cubed is equal to a, we say that 2 is the cube roots of 8. The nth roots of a is the number that, when raised to the nth power, give a. For example, negative 3 is the fifth power. Is the fifth roots of negative 243, because negative 3 to the power of 5 is equal to negative 243. If a is a real number with at least one nth root, then the principal nth roots of a is a number with the same sign as a, that, when raised to the nth power, equals a. The principal nth roots of a is written as n inside the square root of a, where n is a positive integer greater than or equal to 2. In the radical expression, n is called the index of the radical. Principal nth roots. If a is a real number with at least one nth root, then the principal nth roots of a, written as n inside the square root of a, is the number with the same sign as a, that, when raised to the nth power, equals a. The index of the radical is n. Using rational exponents. Radical expression can also be written without using radical symbol. We can use rational fractional exponents. The index must be a positive integer. This is important. If the index n is even, then a cannot be negative. So like this. These things is the same thing. We can also have rational exponents with numerators other than 1. In these cases, the exponents must be a fraction. Sorry, I mistyped it. A fraction in lowest term. We raised the base to a power and take the nth root. The numerator tells us that the power and the denominator tells us the roots. All of the properties of exponents that we learned for integer exponents also hold for rational exponents. Like this thing is the same thing as this also, which is just this one. Rational exponents. Rational exponents are another way to express principal nth roots. The general form for converting between a radical expression with a radical symbol and one with rational exponent is like this. A to the power of m over n is just this thing over here, and also equal to this thing. So let's do some practice question. First one, evaluating square roots. Evaluate each expression. I'll give you guys 30 seconds to work on these, starting from now. Alright, so the answer for these are, the first one is just 10, since 10 squared is equal to 100. The second one, we do like twice the square root. So the square root of 16, which is 4, and then the square root of 4, which is 2. So the answer is 2. And for the third one, when we add 25 and 144, we get 169. And since 13 squared is equal to 169, the square root of 169 is equal to 13, so we get 13. Yeah. And the second practice question. Using the product rule to simplify square roots. Simplify the radical expression. I'll give you guys 30 seconds again for this question. Starting from now. Alright, so the answer for these, the first one is 10 times the square root of 3. Since when we factor the thing out, we get 100 times square root of 100 times square root of 3, which the square root of 100 is just 10, so 10 times the square root of 3. And for the second one, 162 is equal to 81 times 2, so we can just like do this, and then we get 81 times a to the 4th power times b to the 4th power. We can factor that out since just like the square root of 81 is 9. The square root of a to the 4th power is a squared. And the square root of b to the 4th power, it's b squared. And we get 2a left for the inside. So we just multiply them out. So we get 9a squared times b squared times the square root of 2a for this one. Yeah. For the third practice question, using the quotient rule to simplify square roots. Simplify the radical expression. I'll give you guys 30 seconds again for this question, starting from now. Alright, so the answer for the first one, it's just like this. We can, like, this thing over here is the same as square root of 5 over square root of 36. And square root of 36 is just 6. But we cannot further simplify the square root of 5, so we just leave it like that. And we get square root of 5 over 6. And for the second one, when we like take the square like when we factor the numerator and the denominator out, we get 9x to the 4th power, since we can just like subtract 11 by 7, and this is just 1 minus 1, so we don't have any y left, but we got x to the 4th power on top left. And also when we divide 234 by 26, we get 9. So when we factor that out, we get square root of 9 times x to the 4th power. And when we like do the square root of that, we get 3 times x squared. So that's the answer. And here's the fourth practice question. Add or subtract square roots. I'll give you guys 30 seconds again for this question, starting from now. Alright, so here's the answer for the first one. We can rewrite 5 times the square root of 12 as 5 times the square root of 4 times 3. which the square root of 4 is 2, so we can take that out, and we get 5 times 2 times the square root of 3, which is just 10 times the square root of 3. Now the term have the same radicand, so we can just add them up. So we get 12 times the square root of 3. And for the second one, when we simplify this one, we get this thing, and then we can simplify this one to get this thing. And now the term has the same radicand, so we can just subtract it, since the radicand is all like this. So we get 92, since 120 minus 28 is just 92. So we get 92 times the absolute value of a times b squared times the square root of 2 times a times c, like this. And here's practice question 5. Rationalizing a denominator containing a single term. Write it in the simplest form. This one. I'll give you 20 seconds for this one. Starting from now. Alright, so the answer for this one. The radical in the denominator is square root of 10. So multiply the fraction by square root of 10 over square root of 10. Then simplify. So if we multiply this out, we get 10 times 10 is just square root of 10 times square root of 10. On the denominator side is just 10. So when we just multiply by 3, we get 30 on the bottom. And for the top one, we just multiply this out. So we get 2 times the square root of 30. And if we cancel the 2 with 30 and replace the denominator by 15, we get square root of 30 over 15, which is the answer for this one. And that's all for today. Thank you for listening.